Close your eyes for a moment and imagine the coldest place you've ever been. Maybe it was a winter day when the temperature dropped below zero, when your breath turned to fog and your fingers went numb even inside your gloves. Maybe it was standing in front of an open freezer, feeling that rush of icy air. Now multiply that cold by 1,000, by 1,000,000, and you're starting to approach the cold of deep space, far from any star. Space is cold. Not just cold like winter, but cold in a way that's hard to imagine. The temperature of empty space, far from any source of heat, is about minus 455 degrees Fahrenheit, just a few degrees above the coldest temperature possible in the universe, a temperature we call absolute zero. At absolute zero, atoms stop moving. Everything freezes solid. Even the air we breathe would turn into ice crystals and fall to the ground like snow. Now, here's a fact that seems obvious. Planets need stars. Planets need suns. The warmth we feel on Earth, the light that lets plants grow, the energy that drives our weather and our oceans, all of it comes from the sun. Without the sun, Earth would be a frozen ball of ice floating in the darkness. Life would be impossible. Everything would be dead and cold. This is what we've always believed. Planets orbit stars. They receive light and heat from those stars. The closer a planet is to its star, the warmer it is. The farther away, the colder. It's a simple relationship, and it's been true for every planet we've ever known. From Mercury, baking close to the Sun, to Neptune, freezing in the outer solar system. But in the past 2 decades, astronomers have discovered something that shouldn't exist. They found planets floating through space all by themselves, with no star to orbit, no sun to warm them, drifting alone through the cold darkness between the stars. We call them rogue planets, orphan planets, or nomad planets, and they shouldn't be warm. They should be frozen solid, colder than anything we've ever measured, dead worlds lost in the void. Except some of them aren't cold. Some of them are warm, impossibly, inexplicably warm. In fact, astronomers have found rogue planets that are giving off heat, glowing with infrared light, warm enough that if you could somehow stand on their surface, you might not freeze instantly. Some are even warm enough to have atmospheres, to have weather, possibly even to have liquid water hidden beneath their surfaces. These planets have no sun, no star, no obvious source of heat, and yet they're warm. How is this possible? Where is the heat coming from? What could keep a planet warm when it's floating alone in the freezing emptiness of interstellar space, billions of miles from the nearest star? Today, we're going to explore this mystery together. We'll discover how these rogue planets were found, learn about their strange properties, investigate the theories about where their heat comes from, and confront the unsettling possibility that these lonely worlds might not be as dead as we think. Because if a planet can be warm without a sun, if it can generate its own heat through processes we're only beginning to understand, then maybe, just maybe, these dark wanderers could harbor life in places we never thought to look. This is the story of planets that broke free from their stars, worlds that defy our expectations, and the scientists who are trying to understand how something can be warm in the coldest, darkest places in the universe. The story of rogue planets begins with a simple question. When we look out into space, what are we actually seeing? For most of human history, we could only see objects that emit light or reflect light. We could see stars because they generate their own light through nuclear fusion. We could see planets in our solar system because they reflect the sun's light. But what about objects that don't emit light and have no star to reflect? Those objects would be invisible, hidden in the darkness, impossible to find. For a long time, scientists theorized that such objects might exist. When planetary systems form, the process is chaotic and violent. Planets don't just peacefully settle into their orbits. They interact with each other gravitationally. They push and pull, sometimes colliding, sometimes flinging each other into different orbits. Computer simulations of planetary system formation showed that it was common for planets to be ejected entirely, thrown out of their solar systems by gravitational interactions with other planets, sent hurtling into interstellar space with no way to return. These ejected planets would become rogue planets, wandering through the galaxy alone. The simulation suggested that rogue planets might actually be very common, possibly even more common than planets that orbit stars. For every planet we can see orbiting a star, there might be dozens or even hundreds of rogue planets drifting unseen through the darkness. But how do you find something that's invisible? You can't see rogue planets with regular telescopes because they don't emit visible light and they have no nearby star to reflect. For decades, rogue planets remained theoretical mathematical predictions with no observational confirmation. Then, in the 1990s and 2000s, astronomers developed new techniques that could detect objects that don't emit visible light. One of the most important techniques is infrared astronomy. Infrared light is light with wavelengths longer than visible light, the kind of light we feel as heat. Warm objects emit infrared light, even if they don't emit visible light. A human body, for example, emits infrared light, which is why infrared cameras can see people in complete darkness. If rogue planets were even slightly warm, warmer than the background temperature of space, they would emit infrared light. And if astronomers built sensitive enough infrared telescopes, they might be able to detect that light and find these invisible worlds. The breakthrough came with surveys that scanned large areas of the sky looking for faint infrared sources. One of the most successful surveys was conducted using the Canada-France-Hawaii telescope, a large telescope on top of Mauna Kea in Hawaii. Astronomers used this telescope to search young star-forming regions, places where stars and planets had recently formed, looking for objects that emitted infrared light but weren't orbiting any star. In 2000, they found one. It was a small, faint object floating in a star-forming region called the Orion Nebula, about 1,500 light-years from Earth. The object was too small to be a star, not massive enough to ignite nuclear fusion in its core, but it was too far from any star to be a planet in a normal orbit. It was floating alone, drifting through space, and it was glowing faintly in infrared light. This was the first confirmed rogue planet, and astronomers were stunned. The object, which was given a technical designation but no popular name, was about 5 to 15 times the mass of Jupiter, making it either a very massive planet or possibly a brown dwarf, an object that's between a planet and a star in mass. The important point was that it was alone, it was warm, and it shouldn't have been there. Over the next 2 decades, astronomers found more rogue planets. Some were discovered using infrared surveys. Others were found using a technique called gravitational microlensing, which detects planets by the way their gravity bends light from more distant stars. When a rogue planet passes in front of a distant star from our perspective, the planet's gravity acts like a lens, briefly magnifying the star's light. By carefully monitoring millions of stars and looking for these brief brightening events, astronomers can detect rogue planets even though they're too faint to see directly. Microlensing surveys have detected dozens of potential rogue planets, and statistical analysis suggests that there could be billions of them in our galaxy alone, perhaps even trillions. These objects are everywhere, invisible ghosts drifting through space, and we're only just beginning to find them. But here's what's truly strange. Many of these rogue planets are warm. Not all of them, but enough to be surprising. When astronomers measure the infrared light from rogue planets, they can calculate the temperature, and what they find is that some of these planets have temperatures of several hundred degrees Fahrenheit, far warmer than they should be. Remember, space is minus 455 degrees Fahrenheit. A planet floating in interstellar space with no star should cool down to nearly that temperature relatively quickly, at least on astronomical timescales. After a few million years, any heat left over from the planet's formation should have radiated away into space, and the planet should be frozen solid. But these rogue planets aren't frozen. They're warm. Some are warm enough to have atmospheres that haven't frozen and fallen to the surface. Some might even be warm enough to have liquid water, not on the surface where it would immediately boil away into space or freeze, but underground in subsurface oceans insulated from the cold of space by thick layers of ice and rock. This discovery changed everything. It meant that planets didn't need stars to be interesting. It meant that there might be warm, possibly even habitable environments in places we never thought to look. And it meant that we had a lot to learn about how planets work, about where heat comes from, and about the possibilities for life in the universe. To understand why rogue planets are warm, we need to understand where heat comes from in the first place. On Earth, the answer seems obvious. Heat comes from the sun. The sun's light warms our atmosphere and our oceans. It drives our weather. It makes life possible. Without the sun, Earth would be a frozen wasteland. But that's not the whole story. Earth actually has 2 sources of heat. The first is external heat from the sun, and the second is internal heat generated by the planet itself. This internal heat is left over from Earth's formation and is continuously produced by radioactive decay in the planet's interior. When Earth formed 4.5 billion years ago, it was incredibly hot. The process of formation involved countless collisions between smaller objects called planetesimals, chunks of rock and metal that smashed together, releasing enormous amounts of energy. Each collision generated heat. As Earth grew larger, the gravitational energy of infalling material was converted into heat. By the time Earth reached its current size, the planet was so hot that much of it was molten. The surface was covered with oceans of liquid rock, and the interior was a roiling mass of molten iron and silicate. Over billions of years, Earth has been cooling down, radiating this primordial heat away into space. But the cooling is very slow because rock and metal are good insulators, and because the planet is so large. Even today, 4.5 billion years after formation, Earth's interior is still incredibly hot. The core temperature is about 10,000 degrees Fahrenheit, as hot as the surface of the sun. In addition to this leftover heat from formation, Earth generates new heat through radioactive decay. Elements like uranium, thorium, and potassium exist in Earth's crust and mantle, and when their atoms decay, they release energy in the form of heat. This heat adds to the planet's internal temperature and helps keep the interior molten. The combination of primordial heat and radioactive heating means that Earth's interior is hot enough to drive geological processes. The heat causes convection in the mantle, where hot rock slowly rises and cooler rock sinks, creating currents that move the tectonic plates on the surface. This process, plate tectonics, is responsible for earthquakes, volcanoes, mountain building, and the recycling of Earth's crust. It's one of the things that makes Earth geologically active and, indirectly, helps make the planet habitable. Now, let's think about a rogue planet. A rogue planet formed the same way Earth did, through collisions and accretion of material. It started out hot, with a molten interior. If the planet is massive enough, it would also contain radioactive elements that generate heat. So a newly formed rogue planet would have internal heat, just like Earth. The question is, how long does that heat last? How quickly does the planet cool down once it's no longer receiving heat from a star? The answer depends on the planet's size. Smaller planets cool faster because they have less volume relative to their surface area. Heat is stored in the volume of the planet, but is lost through the surface. A small planet has a large surface area relative to its volume, so it loses heat quickly. A large planet has a small surface area relative to its volume, so it retains heat much longer. This is the same reason why a cup of coffee cools faster than a bathtub full of hot water. The cup has a large surface area relative to its volume, so heat escapes quickly. The bathtub has much more volume relative to its surface area, so it stays warm longer. For a planet, the math works out such that Earth-sized planets cool relatively quickly. If Earth were suddenly removed from the sun's heat, the surface would freeze within days. The oceans would turn to ice. The atmosphere would snow out and freeze. But the interior would stay hot for millions of years, gradually cooling as heat worked its way to the surface and radiated into space. For larger planets, like Jupiter-sized gas giants, the cooling is much, much slower. Jupiter has a mass 318 times greater than Earth, and a volume about 1,400 times greater. That's a huge amount of material storing heat, and a relatively small surface area for the heat to escape through. As a result, Jupiter has been cooling for 4.5 billion years, and is still warm. In fact, Jupiter emits more heat into space than it receives from the sun. The planet glows with its own infrared light, powered by internal heat. If Jupiter were suddenly removed from the solar system and became a rogue planet, it would stay warm for billions of years, possibly for the entire future lifetime of the universe. The planet would cool so slowly that it would take longer than the current age of the universe for it to reach the temperature of empty space. This is one of the main reasons why rogue planets can be warm. If they're large enough, like Jupiter or bigger, they retain heat from their formation for incredibly long periods of time, even floating alone in the darkness. Billions of miles from any star, they continue to glow with infrared light, powered by the primordial heat of their birth. But there's more to the story. Some rogue planets might not just be coasting on their formation heat. They might be actively generating new heat through processes that don't require a star. And understanding those processes is key to understanding how these planets can be warm and what that warmth might mean for the possibility of life. Let's focus on one specific rogue planet that has captured scientists' attention and exemplifies the mysteries we're trying to solve. This planet has a technical designation, PSOJ 318.5-22. It's not a catchy name, but it's one of the most studied rogue planets ever discovered. And what we've learned about it is both fascinating and deeply puzzling. PSOJ 318.5-22 was discovered in 2013 by astronomers using the Pan-STARRS 1 telescope in Hawaii. Pan-STARRS, which stands for Panoramic Survey Telescope and Rapid Response System, is designed to scan the sky repeatedly, looking for objects that move or change brightness. It's primarily used to search for asteroids that might pose a threat to Earth, but it also finds all sorts of other interesting objects, including rogue planets. When astronomers analyzed the data from Pan-STARRS, they noticed an object that appeared in multiple images, but wasn't associated with any star. It was moving through space, which meant it was relatively close by in astronomical terms, but there was no star nearby that it could be orbiting. Follow-up observations with other telescopes confirmed that this was indeed a planet-mass object floating alone through space. What makes PSOJ 318.5-22 special is how much we've been able to learn about it. The planet is located about 80 light-years from Earth, which is close enough that we can study it in detail. It's also young, only about 12 million years old. That might sound old, but in astronomical terms, it's an infant. Our solar system is 4.5 billion years old, so PSOJ 318.5-22 is only about 1/400th the age of Earth. Being young means the planet is still quite warm from its formation. When astronomers measured the infrared light from PSOJ 318.5-22, they calculated that its surface temperature is about 1,100 degrees Fahrenheit. That's hot enough to melt aluminum. The planet is glowing red hot, like a piece of metal fresh from a forge, and it's doing this with no star anywhere nearby. The planet's mass is estimated to be about 6 times the mass of Jupiter, making it a super-Jupiter. It's so massive that it's near the boundary between planets and brown dwarfs, those failed stars that aren't quite massive enough to sustain nuclear fusion. Some scientists debate whether PSOJ 318.5-22 should even be called a planet or whether it's better classified as a brown dwarf. For our purposes, we'll call it a planet because it formed like a planet and has properties similar to other planetary mass objects. One of the most intriguing things about PSOJ 318.5-22 is its atmosphere. Using spectroscopy, the technique of splitting light into its component wavelengths to identify what elements and molecules are present, astronomers have detected water vapor in the planet's atmosphere. They've also found evidence of methane, carbon monoxide, and possibly other compounds. The atmosphere is thick and turbulent, with massive storms and weather systems driven by the planet's internal heat. Think about that for a moment. Here's a planet floating alone in the darkness, with no sun, and it has an atmosphere with weather. Clouds form and dissipate. Storms rage across its surface. Lightning might crackle through the clouds, though we haven't detected that yet. All of this is happening on a world that's completely isolated from any star, lit only by the faint glow of its own heat. What's even more remarkable is that PSOJ 318.5-22 appears to have a magnetic field. Observations have detected radio emissions from the planet, similar to the radio emissions that Jupiter produces. These emissions are generated by charged particles spiraling along magnetic field lines, a process that requires a strong magnetic field and a source of energetic particles. On Jupiter, the magnetic field is generated by a dynamo process in the planet's interior, where metallic hydrogen flows and creates electric currents. If PSOJ 318.5-22 has a magnetic field, it means the interior of the planet is dynamic and active. Heat is flowing through the interior, creating convection currents, and these currents are generating a magnetic field. This is exactly what happens inside Earth and Jupiter, but it's happening on a planet with no star, powered entirely by internal heat. The existence of a magnetic field is important for several reasons. First, it tells us that the planet's interior is hot and liquid, not frozen solid. Second, it shows that the planet has complex internal structure, with different layers and regions where different processes are happening. Third, it raises the intriguing possibility that the magnetic field could protect any potential atmosphere or surface features from being stripped away by cosmic rays and interstellar radiation. But here's the mystery. PSOJ 318.5-22 is warm now, but how long will it stay warm? The planet is only 12 million years old, so it's still glowing with the heat of its formation. As it ages, it will cool down. In a few 100 million years, maybe 1 billion years, the surface temperature will drop significantly. Eventually, after billions of years, the planet will cool to the temperature of empty space, and it will become a frozen, dead world drifting silently through the darkness. Unless there's another source of heat. Unless there's a process we don't fully understand that keeps generating heat even as the planet ages. And this is where the story gets really interesting. BECAUSE, scientists have discovered several mechanisms that could generate heat in rogue planets. Mechanisms that don't require a star, and that could potentially keep a planet warm for billions of years. One of the most exciting possibilities about warm rogue planets is that they might have liquid water, not on the surface, where it would immediately freeze or boil away into the vacuum of space, but hidden beneath thick layers of ice, insulated from the cold above and warmed by heat from below. This idea isn't just speculation. We have examples of this kind of environment right here in our own solar system. Europa, one of Jupiter's moons, is covered in a thick shell of ice, but beneath that ice is believed to be a global ocean of liquid water. The ocean stays liquid because of tidal heating. Europa's orbit around Jupiter isn't perfectly circular, so the gravitational pull from Jupiter varies as the moon orbits. This variation causes Europa to flex and stretch, generating heat through friction, and that heat keeps the subsurface ocean from freezing. Another example is Enceladus, a small moon of Saturn. Despite being much smaller than Europa and much farther from the Sun, Enceladus also has a subsurface ocean. We know this because the Cassini spacecraft observed geysers erupting from Enceladus's south polar region, shooting plumes of water vapor and ice particles into space. The only way those geysers could exist is if there's liquid water beneath the ice, and the only way the water could stay liquid is if there's a heat source inside the moon. If moons can have subsurface oceans, why not rogue planets? A large rogue planet, especially one with significant internal heat from radioactive decay and leftover formation heat, could maintain a subsurface ocean for billions of years. The ice layer on top would act as insulation, trapping the heat inside and preventing it from radiating into space. The thicker the ice, the better the insulation. Let's imagine what such a planet might look like. On the surface, it would be a world of ice, frozen solid, with temperatures close to absolute zero. The ice could be miles or even tens of miles thick, clear in some places, opaque in others, sculpted by slow geological processes into ridges, cracks, and flat plains. There would be no sunlight, no day or night, just eternal darkness lit only by the faint glow of distant stars and the occasional cosmic ray shower, creating brief flashes of light in the ice. But beneath that ice, in the darkness below, there could be an ocean. The water would be kept liquid by heat, rising from the planet's interior. The temperature might be just above freezing, or it could be much warmer, depending on how much heat is being generated and how efficiently it's transported to the ocean. There could be currents in the ocean, driven by temperature differences, carrying heat from warmer regions to cooler ones. There could be chemical gradients with different concentrations of salts and minerals in different parts of the ocean. And here's where it gets truly exciting. There could be life. On Earth, we find life in the deepest, darkest parts of the ocean, in places where no sunlight reaches. These ecosystems are powered not by photosynthesis, but by chemosynthesis, where microorganisms extract energy from chemicals dissolved in the water. Near hydrothermal vents on the ocean floor, where hot water rich in minerals gushes up from cracks in Earth's crust, entire communities of organisms thrive in complete darkness. If a rogue planet has a subsurface ocean, and if that ocean has chemical energy available, similar chemosynthetic life could potentially exist there. The life forms would be completely different from anything we know, adapted to eternal darkness, extreme cold, and isolation from any star, but they could exist. The laws of chemistry and biology don't require sunlight. They only require liquid water, chemical energy, and time. This isn't just wild speculation. Scientists are seriously considering the possibility, and some are even designing missions to search for life on rogue planets. The challenge is detection. How do you find a subsurface ocean on a planet you can barely see? How do you determine if that ocean harbors life? One approach is to look for signs of geological activity. If a rogue planet has a subsurface ocean, there might be cryovolcanoes on the surface, similar to the geysers on Enceladus. These would be volcanoes that erupt not with molten rock, but with liquid water or slush. The water would immediately freeze in the vacuum of space, creating plumes of ice particles that could be detected by telescopes. Another approach is to study the planet's infrared spectrum carefully. Different minerals and ices have different infrared signatures, and by analyzing the spectrum, scientists can infer what materials are present on the surface and in the atmosphere. If they detect certain patterns that suggest recent volcanic or cryovolcanic activity, that would be evidence of internal heat and possibly a subsurface ocean. There's also the possibility of detecting biosignatures, chemicals that are produced by life. On Earth, oxygen in the atmosphere is a biosignature because it's produced by photosynthetic organisms. For a rogue planet, different biosignatures might be relevant, like methane or other organic molecules that could be produced by chemosynthetic life and released into the atmosphere through cryovolcanic eruptions. All of this is speculative for now, but it's based on solid science and real observations of moons in our solar system. If moons like Europa and Enceladus can have subsurface oceans, there's no reason rogue planets can't. And if those oceans exist, they represent entirely new environments where life might arise. Environments we never would have imagined just a few decades ago. The hidden oceans theory is one explanation for why rogue planets might be warm, and one reason why scientists are so excited about studying them. These aren't just dead, frozen worlds. They might be dynamic, geologically active, and possibly even inhabited. We've talked about primordial heat, the leftover warmth from a planet's formation. But there's another source of internal heat that's even more reliable and long-lasting: radioactive decay. This process has been keeping Earth's interior hot for billions of years, and it could be doing the same for rogue planets, providing a steady source of heat that doesn't depend on a star. Radioactive decay is a natural process where unstable atomic nuclei break apart, releasing energy. The atoms of certain elements, like uranium-238, thorium-232, and potassium-40, are naturally unstable. Over time, they spontaneously decay, transforming into different elements and releasing particles and radiation in the process. This radiation is absorbed by the surrounding material, heating it up. The heat generated by radioactive decay is small on a human scale, but enormous when you're talking about an entire planet. Earth contains trillions upon trillions of tons of radioactive elements, distributed throughout the crust, mantle, and core. Every second, countless atoms are decaying, and the cumulative heat from all those decays is substantial. Scientists estimate that about half of the heat flowing from Earth's interior today comes from radioactive decay. The other half is leftover primordial heat. The beautiful thing about radioactive decay is that it's incredibly long-lived. Radioactive elements decay at a rate characterized by their half-life, the time it takes for half of a given sample to decay. Uranium-238 has a half-life of 4.5 billion years, which is about the age of Earth. This means that half of the uranium-238 that was present when Earth formed is still here today, still decaying, still generating heat. Thorium-232 has a half-life of 14 billion years, even longer than the current age of the universe. Potassium-40 has a half-life of 1.25 billion years. Because these half-lives are so long, radioactive decay provides a heat source that lasts for billions of years. A planet rich in radioactive elements will stay warm internally for an incredibly long time, far longer than it would stay warm from primordial heat alone. Now, let's apply this to rogue planets. When a rogue planet forms, it incorporates whatever elements were present in the disk of gas and dust from which it formed. If that disk contained radioactive elements, and it almost certainly did, because these elements are produced in supernova explosions and distributed throughout the galaxy, then the planet will contain radioactive elements in its interior. The amount of radioactive elements depends on the planet's composition and where it formed. Rocky planets like Earth have relatively high concentrations of uranium, thorium, and potassium because these elements tend to concentrate in rocky material. Gas giants like Jupiter have lower concentrations because most of their mass is hydrogen and helium, which don't contain radioactive isotopes. But even gas giants have rocky cores, and those cores can contain significant amounts of radioactive material. For a rogue planet, the heat from radioactive decay could be enough to keep the interior warm for billions of years. This is especially true if the planet is large, because larger planets have more radioactive material in total, and because they lose heat more slowly due to their smaller surface area to volume ratio. Imagine a rogue planet with a rocky core the size of Earth, rich in uranium and thorium. The core is generating heat through radioactive decay, and that heat is slowly working its way to the surface. If the planet has a thick mantle and crust, the heat gets trapped, keeping the interior hot. If there's a subsurface ocean, as we discussed in the last chapter, the heat from radioactive decay warms the ocean, keeping it liquid. This heat source is stable and reliable. It doesn't depend on the planet's orbit or its distance from any star. It doesn't fluctuate or vary. It's just there, steadily generating heat year after year, century after century, for billions of years. Some scientists have calculated that a rogue planet with the right composition could maintain a subsurface ocean for the entire lifetime of the galaxy, tens of billions of years, powered entirely by radioactive decay. This is mind-blowing when you think about it. A planet could be drifting through space for longer than the sun will exist, and it could still have liquid water and possibly life, all thanks to the steady fire of radioactive atoms deep in its core. Of course, there are complications. The rate of heat generation from radioactive decay decreases over time as the radioactive elements decay and are not replaced. After several billion years, the heat generation rate is lower than it was at the beginning. Also, the efficiency of heat retention depends on the planet's structure. If the planet has a thin crust, heat escapes quickly. If it has a thick crust and a layer of insulating ice, heat is retained much better. But the basic principle is sound. Radioactive decay can keep a rogue planet warm for an incredibly long time. Combined with primordial heat, it provides a heat budget that can sustain geological activity, subsurface oceans, and possibly even life, all without any contribution from a star. This is why scientists are so interested in studying the composition of rogue planets. If we can determine how much uranium, thorium, and potassium they contain, we can estimate how long they'll stay warm and whether they're likely to have habitable subsurface environments. This is difficult to do with current technology because we can't directly sample a rogue planet's interior, but we can make educated guesses based on models of planetary formation and observations of the planet's density and overall composition. The radioactive decay mechanism is one of the most robust explanations for why rogue planets are warm. It's not exotic or speculative. It's a well-understood process that we know operates on Earth and other planets. The only question is how much of this heat source any given rogue planet has and how efficiently it retains that heat. Another factor that can keep a rogue planet warm, or at least prevent it from cooling as quickly as it otherwise would, is the atmosphere. A thick atmosphere can act like a blanket, trapping heat and preventing it from radiating into space. This is the same greenhouse effect that keeps Earth warmer than it would be without an atmosphere. And it could work on rogue planets too, especially if they have the right kind of atmosphere. Let's start with the basics of how atmospheres retain heat. When a planet radiates heat, it does so primarily in the form of infrared light. This is the same kind of light you feel as heat from a warm stove. The heat from the planet's surface and interior is converted into infrared photons, which then travel outward into space. If the planet has no atmosphere, or only a very thin atmosphere, these infrared photons escape freely into space, and the planet cools quickly. But if the planet has a thick atmosphere, especially one containing certain gases, those gases can absorb the infrared photons. When a gas molecule absorbs an infrared photon, it gains energy and vibrates more. Eventually, the molecule re-emits the photon, but in a random direction. Some of these re-emitted photons go back down toward the surface, while others continue upward. The result is that energy gets trapped in the atmosphere. The infrared photons bounce around, getting absorbed and re-emitted multiple times before finally escaping into space. This process slows down the rate at which the planet loses heat, keeping the surface warmer than it would be otherwise. This is the greenhouse effect. On Earth, greenhouse gases like carbon dioxide, water vapor, and methane are responsible for keeping the planet about 60 degrees Fahrenheit warmer than it would be without them. Without the greenhouse effect, Earth's average temperature would be below freezing, and the planet would be covered in ice. So the greenhouse effect is not inherently bad. It's actually essential for life as we know it. The problem arises when greenhouse gas concentrations increase too much, causing temperatures to rise beyond historical norms, as we're seeing with human-caused climate change. For a rogue planet, the greenhouse effect could work the same way, but with some important differences. First, the planet doesn't have an external heat source like the sun, so the only heat being trapped is the internal heat generated by radioactive decay and leftover from formation. Second, the composition of the atmosphere matters a lot. Some gases are much better at trapping infrared radiation than others. Hydrogen and helium, which make up most of the atmospheres of gas giant planets like Jupiter, are actually not very good greenhouse gases. They're transparent to infrared radiation, so they don't trap much heat. But other gases like methane, carbon dioxide, ammonia, and water vapor are excellent greenhouse gases. If a rogue planet has an atmosphere rich in these gases, it could retain heat very effectively. There's another factor to consider: atmospheric pressure. A thick, dense atmosphere provides more insulation than a thin one, simply because there are more molecules to absorb and re-emit infrared photons. A rogue planet with a very thick atmosphere, even if it's made mostly of hydrogen and helium, could still retain some heat just due to the sheer density of the gas. Some theoretical models have explored what would happen if a rogue planet had an extremely thick hydrogen atmosphere, one with surface pressures thousands or even millions of times greater than Earth's atmospheric pressure. At such high pressures, hydrogen can act as an effective insulator, trapping heat through a process called pressure-induced opacity. The hydrogen molecules are packed so tightly that they interact with each other in ways that allow them to absorb infrared radiation. In these models, a rogue planet with the right combination of internal heat generation and atmospheric thickness could maintain surface temperatures above freezing, at least for a while. The planet wouldn't be warm by Earth standards, but it could be warm enough to have liquid water on the surface, not just underground. This is a speculative scenario, and we don't know if such planets actually exist, but it's within the realm of physical possibility. The universe is full of surprises, and we've learned not to assume that what we see in our solar system represents all the possibilities. There's also the question of how long an atmosphere lasts on a rogue planet. Atmospheres can escape into space, especially on smaller planets with weaker gravity. The process is called atmospheric escape, and it's driven by various mechanisms. High-energy particles, like cosmic rays, can strike atoms in the upper atmosphere and give them enough energy to escape. Thermal escape can occur if the atmosphere is hot enough that some molecules reach escape velocity. And without a magnetic field to protect it, a planet's atmosphere is more vulnerable to being stripped away by the interstellar medium. For a large, massive rogue planet with a strong magnetic field, atmospheric escape would be slow. The planet's gravity would hold onto the atmosphere, and the magnetic field would deflect incoming cosmic rays. Such a planet could retain its atmosphere for billions of years, providing long-term insulation and contributing to the planet's warmth. For a smaller planet, atmospheric escape could be faster, and the atmosphere might be lost over millions or hundreds of millions of years. Once the atmosphere is gone, the planet would cool much more quickly, losing whatever greenhouse warming it had. Understanding the interplay between internal heat, atmospheric composition, and atmospheric retention is crucial for understanding how warm rogue planets can be and how long they can stay warm. It's a complex system with many variables, and scientists are still working to model it accurately. But the key point is this: a thick atmosphere can make a significant difference. It can extend the time a rogue planet stays warm, create more favorable conditions for subsurface oceans, and possibly even allow for surface habitability in some extreme cases. The atmosphere is not just a passive layer of gas. It's an active participant in the planet's thermal evolution. As we study rogue planets, especially the massive ones, we keep running into a boundary problem. At what point does a planet stop being a planet and start being something else? This question leads us to brown dwarfs, objects that are between planets and stars in mass. And understanding brown dwarfs helps us understand warm rogue planets. Brown dwarfs are sometimes called failed stars because they're not massive enough to sustain hydrogen fusion in their cores, the process that powers normal stars like the Sun. Hydrogen fusion requires extremely high temperatures and pressures, which only occur in objects above a certain mass, about 75 to 80 times the mass of Jupiter. Below that threshold, the object never gets hot enough to ignite hydrogen fusion, and it becomes a brown dwarf instead of a star. Brown dwarfs are strange objects. They're much more massive than planets, typically ranging from 13 to 75 Jupiter masses. The lower bound, 13 Jupiter masses, is significant because that's the mass at which objects can fuse deuterium, a heavier form of hydrogen. Below 13 Jupiter masses, even deuterium fusion is not possible, and we generally call those objects planets. Above 13 Jupiter masses, deuterium fusion can occur, at least temporarily, and we call them brown dwarfs. But the distinction is blurry, and it's based on mass alone, which might not be the most meaningful way to categorize objects. An object that forms like a planet from a disk around a star, but happens to be 15 Jupiter masses. Is it a planet or a brown dwarf? An object that forms like a star from the collapse of a gas cloud, but happens to be only 10 Jupiter masses. Is it a brown dwarf or a planet? These questions don't have clear answers, and astronomers debate them constantly. What's relevant for our story is that brown dwarfs are warm for the same reasons rogue planets are warm. They have internal heat from their formation, and they're large enough to retain that heat for billions of years. In fact, brown dwarfs can stay warm longer than most planets because they're more massive. When brown dwarfs are young, they can be quite hot, with surface temperatures of thousands of degrees. As they age, they cool down, but very slowly. Even after billions of years, old brown dwarfs still have surface temperatures of several hundred degrees, warm enough to emit significant infrared light. Astronomers have studied brown dwarfs extensively because they're easier to find and study than rogue planets. They're more massive, so they're brighter in infrared light, and thousands have been discovered. By studying brown dwarfs, scientists have learned a lot about how objects without nuclear fusion cool and evolve over time. And many of these lessons apply to massive rogue planets as well. One interesting finding is that brown dwarfs have weather. They have atmospheres with clouds, storms, and temperature variations. Some brown dwarfs show evidence of banded structures, like the bands on Jupiter, suggesting organized atmospheric circulation. They also have magnetic fields and can produce radio emissions, just like planets. In many ways, brown dwarfs are like scaled-up versions of gas giant planets, and the most massive rogue planets are like scaled-down versions of brown dwarfs. There's a continuum of objects from Jupiter-mass planets to stellar-mass stars, and brown dwarfs and massive rogue planets sit right in the middle of that continuum. This connection is important because it means we can use what we learn about brown dwarfs to inform our understanding of rogue planets and vice versa. If brown dwarfs can stay warm for billions of years with no external heat source, then so can massive rogue planets. If brown dwarfs have complex atmospheres and magnetic fields, then massive rogue planets probably do too. There's also a practical consequence. Some of the objects we've been calling rogue planets might actually be brown dwarfs that formed in isolation, not from a planetary disk, but from the direct collapse of a small gas cloud. Distinguishing between these two formation pathways is difficult because once the object exists, it looks the same regardless of how it formed. Astronomers try to use context and statistical arguments to figure out which objects are planets and which are brown dwarfs. If an object is found floating alone, but is located in or near a star-forming region, it was probably born there through a star-like formation process, making it a brown dwarf. If an object is found far from any star-forming region and has properties consistent with being ejected from a planetary system, it's probably a rogue planet. But these are educated guesses, not definitive answers. The truth is, we don't always know what we're looking at, and that ambiguity is part of what makes this field so exciting and challenging. From a practical standpoint, for understanding warmth, it doesn't matter much whether we call an object a massive rogue planet or a low-mass brown dwarf. What matters is its mass, composition, and age, because those factors determine how warm it is and how long it stays warm. The labels we use are somewhat arbitrary, convenient categories for organizing our knowledge, but nature doesn't care about our labels. The brown dwarf connection reminds us that the universe is not neatly divided into distinct categories. There are gradients, spectra, continuums of properties. And sitting somewhere on that continuum are warm rogue planets, objects that blur the lines between planet, brown dwarf, and star, challenging us to think more deeply about what those categories really mean. Here's a twist in the story that not many people know about. Some rogue planets might not be alone. They might have moons, or they might be part of binary systems where two planet-mass objects orbit each other. And if that's the case, there's another mechanism that can generate heat: tidal heating. We've already talked about tidal heating in the context of Jupiter's moon Europa. Europa's orbit around Jupiter is slightly elliptical, so the gravitational pull from Jupiter varies, causing Europa to flex and generating heat through friction. This tidal heating keeps Europa's subsurface ocean liquid, despite being far from the sun. The same process can work in a rogue planet system. Imagine a rogue planet with a large moon. The planet and moon orbit their common center of mass, and if the moon's orbit is elliptical, the tidal forces between them will vary, causing both objects to flex and heat up internally. Or imagine two planet-mass objects that were ejected from their star system together and now orbit each other as a binary system. They're both rogue, floating through interstellar space, but they're gravitationally bound to each other. If their orbits are elliptical, they'll experience tidal heating, generating warmth that doesn't come from radioactive decay or leftover formation heat. Tidal heating can be incredibly powerful. On Io, the innermost large moon of Jupiter, tidal heating is so intense that it drives hundreds of active volcanoes. Io is the most volcanically active object in the solar system, with eruptions constantly resurfacing the moon and ejecting plumes of sulfur dioxide hundreds of miles into space. All of this energy comes from tidal heating caused by Jupiter's gravity and orbital resonances with other moons. For a rogue planet binary system, tidal heating could generate enough heat to maintain subsurface oceans, drive geological activity, and keep the objects warm for as long as the tidal interactions continue. The key is that the orbits need to be eccentric, not circular. If the orbits are perfectly circular, the tidal forces are constant, no flexing occurs, and no heat is generated. But maintaining an eccentric orbit requires something to prevent the orbit from circularizing. In the Jupiter system, orbital resonances with other moons keep Europa's orbit eccentric. For a rogue binary system, the situation is more delicate. Over time, tidal interactions tend to circularize orbits and synchronize rotations. Eventually, both objects would become tidally locked, always showing the same face to each other, and the orbit would become circular. At that point, tidal heating would stop. How long this process takes depends on the masses and distances involved. For massive objects close together, circularization can happen relatively quickly, in millions or tens of millions of years. For less massive objects farther apart, it could take billions of years. So tidal heating in a rogue binary system is potentially a long-term heat source, but not necessarily as long-term as radioactive decay. There's an interesting related scenario: a rogue planet with multiple moons in orbital resonances with each other. Resonances occur when the orbital periods of two objects are related by a simple ratio, like 2:1 or 3:2. In resonance, the moons regularly pass close to each other. Their gravitational interactions reinforce, and eccentricities can be maintained or even amplified. The Jupiter system is a great example. The moons Io, Europa, and Ganymede are in a 4:2:1 resonance. For every orbit Ganymede makes, Europa makes 2, and Io makes 4. This resonance keeps Europa's orbit eccentric, enabling the tidal heating that maintains its subsurface ocean. A rogue planet with a similar moon system could have sustained tidal heating for billions of years, providing a reliable heat source that supplements radioactive decay. The moons would be warm worlds with geological activity, possibly with subsurface oceans, all orbiting a dark planet that itself might be warm from internal heat. We haven't yet detected any moons around rogue planets, but that's not surprising. Moons are much smaller and fainter than planets, and detecting them around an already faint rogue planet is extremely difficult with current technology. But there's no reason they shouldn't exist. Planets in our solar system have moons, many of them large and interesting. Rogue planets probably have moons too. If we could find a rogue planet with a moon, and especially if we could find evidence of tidal heating, that would be a major discovery. It would open up new possibilities for habitability on rogue objects and give us new targets to search for life. Some scientists have proposed that the best places to look for life in the galaxy might not be planets orbiting stars, but moons orbiting rogue planets. These moons would be heated by tidal interactions, protected from harmful radiation by the planet's magnetic field, and stable over long timescales. They would be oases of warmth and energy in the cold darkness, hidden from view, but potentially teeming with life. It's a beautiful idea, and it's scientifically plausible. Whether such systems actually exist and whether they harbor life are questions we can't answer yet, but they're questions worth pursuing. To understand rogue planets and their thermal evolution, scientists rely heavily on computer simulations. We can't visit these planets, we can't measure their interiors directly, and we can only observe a handful of them with current technology. So we build mathematical models, code them into computers, and simulate how rogue planets form, evolve, and cool over billions of years. These simulations are complex, involving physics from multiple disciplines. You need to model gravity, thermodynamics, fluid dynamics, radiative transfer, chemical reactions, phase transitions, and more. The simulations require powerful supercomputers and sophisticated algorithms, and even then, they're simplifications of reality. But they're the best tools we have for exploring scenarios that we can't test experimentally. One of the key things scientists want to understand is how quickly rogue planets cool. The cooling rate determines how long a planet stays warm enough to have liquid water and potentially support life. It also determines the observable properties of the planet, like its infrared brightness, which is what allows us to detect it in the first place. To model cooling, you need to know several things. First, the planet's initial temperature, which depends on how it formed and whether it underwent any giant impacts or other energetic events during formation. Second, the planet's composition, including the amounts of rock, ice, and gas, and the concentrations of radioactive elements. Third, the planet's structure, including whether it has a core, mantle, and crust, and what the thermal properties of these layers are. Fourth, the planet's atmosphere, if it has one, including its thickness and composition. With all these inputs, the simulation tracks how heat flows from the interior to the surface and how it's radiated into space. Over millions and billions of simulated years, the planet cools, and the simulation records how temperature, pressure, and other properties change over time. The results of these simulations have been revealing. For Jupiter-mass planets, the simulations confirm that internal heat can keep the planet warm for billions of years. A planet that starts out with a surface temperature of several thousand degrees will cool to about 1,000 degrees after 100 million years, then to about 500 degrees after a billion years, and continue cooling gradually after that. Even after 10 billion years, longer than the current age of the universe, the planet would still be several hundred degrees above absolute zero. For Earth-mass planets, the cooling is faster because of the smaller size. An Earth-mass rogue planet would lose its surface heat within thousands of years and would become a frozen ice ball. But the interior could stay warm for much longer, especially if there's significant radioactive heating. Simulations show that an Earth-mass rogue planet with Earth-like composition could maintain a subsurface liquid ocean for several billion years, provided the ocean is insulated by a thick ice shell. These simulations have also explored the effects of different atmospheric compositions. A rogue planet with a thick hydrogen atmosphere cools more slowly than one with no atmosphere. A planet with a hydrogen-helium atmosphere, supplemented with greenhouse gases like methane and ammonia, cools even more slowly. The atmosphere acts as a blanket, and the thicker and more opaque the blanket, the better it retains heat. One particularly interesting result from simulations is that there's a sweet spot in planet size for long-term habitability. Planets that are too small cool too quickly and lose their atmospheres. Planets that are too large have such strong gravity that the atmospheric pressure at the surface becomes crushingly high, possibly preventing liquid water from existing. The sweet spot is somewhere around a few times Earth's mass, large enough to retain heat and atmosphere for billions of years, but not so large that surface conditions are hostile. Simulations have also looked at the possibility of surface habitability on rogue planets. Could a rogue planet with the right combination of properties maintain liquid water on its surface? The answer seems to be yes, but only under very specific and perhaps unlikely conditions. The planet would need a very thick hydrogen atmosphere, sufficient internal heating, and a delicate balance between heat generation and heat loss. Such planets, if they exist, would be rare, but the fact that they're possible at all is remarkable. Another finding from simulations is that rogue planets can have plate tectonics, at least for a while. Plate tectonics on Earth is driven by internal heat, which causes convection in the mantle. The convection currents drag the tectonic plates across the surface, creating earthquakes, mountains, and ocean trenches. For a rogue planet with sufficient internal heat, the same process could occur. Plate tectonics is thought to be important for habitability because it recycles chemicals, regulates atmospheric composition, and creates diverse geological environments. However, plate tectonics requires a specific balance of temperature, pressure, and material properties, and it's not clear whether rogue planets typically have the right conditions. Earth is the only planet we know for certain has plate tectonics, though there's some evidence that Venus might have had it in the past, that Mars might have had a form of it early in its history. Whether rogue planets commonly have plate tectonics is an open question, but simulations suggest it's possible. Computer simulations are not perfect. They rely on assumptions and approximations, and there are many physical processes that are not fully understood and therefore difficult to model accurately. But they're improving constantly as we learn more from observations and as computing power increases. The simulations give us predictions that can be tested against observations, and when the predictions match the observations, we gain confidence that our understanding is on the right track. When they don't match, we learn that we're missing something, and we go back to refine the models. The simulations have given us a framework for understanding warm rogue planets. They've shown us that these planets are not mysterious or impossible. They're natural consequences of planetary physics. They've identified the key factors that determine how warm a rogue planet is and how long it stays warm. And they've pointed the way toward future observations that could test the theoretical predictions and refine our understanding even further. Finding rogue planets is one of the hardest challenges in astronomy. These objects are small, faint, and isolated. They don't emit visible light, and they don't orbit stars that would make them easier to detect. They're cosmic needles in an enormous haystack. And yet, astronomers have developed several clever techniques to find them, and new technologies promise to find many more in the coming years. The most successful technique so far has been infrared surveys. As we've discussed, warm rogue planets emit infrared light. By systematically scanning large areas of the sky with infrared-sensitive telescopes, astronomers can identify point sources of infrared light that aren't associated with any star. These candidates can then be followed up with more detailed observations to confirm they're rogue planets and to characterize their properties. Several surveys have contributed to the discovery of rogue planets. The Wide Field Infrared Survey Explorer, or WISE, was a NASA space telescope that surveyed the entire sky in infrared wavelengths from 2010 to 2011. WISE discovered thousands of brown dwarfs and several candidate rogue planets. Its successor, NEOWISE, continues to operate and make discoveries. Ground-based surveys like Pan-STARRS and the upcoming Vera C. Rubin Observatory are also searching for rogue planets. These telescopes take repeated images of the sky, looking for objects that move relative to the background stars. Rogue planets that are relatively nearby will show motion over time, allowing them to be distinguished from more distant stars and galaxies. Another powerful technique is gravitational microlensing. This method doesn't detect the planet's light directly, but instead detects the gravitational effect the planet has on light from more distant stars. When a rogue planet passes in front of a background star from our perspective, the planet's gravity bends the star's light, acting like a magnifying lens and briefly making the star appear brighter. By monitoring millions of stars and watching for these brief brightening events, astronomers can detect rogue planets even though they're too faint to see directly. Microlensing surveys have detected several dozen events that appear to be caused by rogue planets. The technique is particularly sensitive to planets with masses around Earth's mass or a bit larger, which is exciting because those are the planets most likely to have subsurface oceans and possibly habitability. The downside is that microlensing events are one-time occurrences. Once the planet has passed in front of the star and moved on, you can't observe it again, so you can't study it in detail. Despite these limitations, microlensing has provided valuable statistical information. By analyzing the number and properties of microlensing events, scientists can estimate how many rogue planets there are in the galaxy and what the distribution of masses is. The results suggest that there could be billions of rogue planets, possibly outnumbering stars. For every star in the Milky Way, there might be one or more rogue planets. That's an astonishing number. and it means that rogue planets are a major component of the galaxy's population. Looking to the future, several new missions and telescopes will dramatically improve our ability to find and study rogue planets. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct extensive microlensing surveys and could discover thousands of rogue planets, including many Earth mass objects. Roman will also be able to do follow-up observations in some cases, measuring the planet's temperatures and possibly detecting atmospheres. The James Webb Space Telescope, which began operations in 2022, can study the atmospheres of rogue planets in exquisite detail. For the brightest and closest rogue planets, Webb can take spectra that reveal the chemical composition of the atmosphere, the temperature structure, and possibly even biosignatures if they're present. Webb is primarily designed for other purposes, like studying distant galaxies and the early universe, but it can also contribute to rogue planet science when opportunities arise. There are also proposals for dedicated rogue planet missions. One concept is a space telescope optimized for infrared imaging that would survey large swaths of the sky, looking specifically for nearby rogue planets. Another concept is an interferometer, an array of telescopes working together to achieve very high resolution, which could image the surfaces of nearby rogue planets and look for signs of geological activity. Ground-based telescopes are also becoming more capable. The next generation of extremely large telescopes, with mirrors 30 to 40 meters across, will begin operations in the late 2020s and early 2030s. These behemoths will be able to detect much fainter objects than current telescopes, and they'll have advanced instruments for spectroscopy and imaging. They could potentially detect rogue planets within a few tens of light years of Earth and study them in unprecedented detail. All of these technological advances mean that the study of rogue planets is transitioning from finding a few interesting examples to conducting systematic surveys and building up a large sample. With enough examples, we can understand the population as a whole, not just individual objects. We can figure out how common worn rogue planets are, what range of properties they have, and which ones are most likely to be habitable. The search for rogue planets is also motivating theoretical work. As we find more objects, we can test our models against observations and refine our understanding. The interplay between observation and theory is what drives science forward, and we're at an exciting point where both are advancing rapidly. This is the question that haunts and excites scientists in equal measure. We've established that rogue planets can be warm, that they can have subsurface oceans, that they can have atmospheres and geological activity. But can they have life? Can life exist without a sun? In the cold darkness of a world floating alone through interstellar space? To answer this question, we need to think carefully about what life requires. On Earth, almost all life ultimately depends on the sun. Plants use sunlight for photosynthesis, converting light energy into chemical energy. Animals eat plants or eat other animals that eat plants. The entire food web is built on a foundation of sunlight. But there are exceptions. In the deepest parts of the ocean, far below where sunlight can penetrate, there are ecosystems based on chemosynthesis instead of photosynthesis. Near hydrothermal vents, where superheated water, rich in minerals, gushes up from cracks in the Earth's crust. Bacteria harvest energy from chemical reactions. They oxidize hydrogen sulfide or other chemicals dissolved in the water, using the energy to build organic molecules. These bacteria form the base of a food web that includes giant tube worms, clams, crabs, fish, and other organisms, none of which have ever seen sunlight. These deep-sea ecosystems prove that life doesn't need sunlight. It needs liquid water, chemical energy, and the right building blocks. But the energy doesn't have to come from a star. And if life can exist in the darkness of Earth's deep ocean, why not in the darkness of a rogue planet's subsurface ocean? Let's imagine what such an ecosystem might look like. Deep beneath the frozen surface of a rogue planet, in a lightless ocean warmed by heat from the planet's core, there are hydrothermal vents where hot water rich in minerals and dissolved gases rises from below. Bacteria cluster around these vents, feeding on the chemicals. They're the primary producers, the base of the food web. Other organisms have evolved to eat the bacteria. Perhaps they're simple filter feeders, drifting through the water and straining out bacteria. Or perhaps they're more complex, actively hunting and grazing. Over millions of years of evolution, the ecosystem diversifies. There are scavengers that feed on dead organic matter sinking from the upper layers of the ocean. There are predators that hunt other organisms. There might even be large, complex creatures analogous to fish or jellyfish, adapted to the darkness and the cold. All of this is speculation, but it's speculation based on what we know about life on Earth. Life is incredibly adaptable. It's been found in every environment on Earth, where there's liquid water, from the hottest hot springs to the coldest Antarctic ice, from the most acidic lakes to the most alkaline soda lakes, from the highest mountains to the deepest ocean trenches. Life finds a way. The question is not whether life could exist without a sun, but whether it would arise in the first place. The origin of life is one of the great unsolved mysteries in science. We don't know exactly how life began on Earth, though we have many theories and some experimental evidence. We know it requires certain conditions: liquid water, a source of energy, organic molecules, and time. Given enough time and the right conditions, the chemical reactions that lead to life seem to be, if not inevitable, at least reasonably likely. A rogue planet with a subsurface ocean could provide all the necessary conditions. There's liquid water, warmed by internal heat. There's chemical energy from minerals dissolved in the water, and from reactions between the water and the rocky ocean floor. There are organic molecules, either formed locally or delivered by impacts from comets and asteroids. And there's time, billions of years of stability if the heat source lasts. The one thing that might be missing is complexity. On Earth, life began relatively quickly, within the first billion years after the planet formed. But it took much longer for complex, multicellular life to evolve. For over 3 billion years, life on Earth consisted only of single-celled organisms. Complex life, including animals and plants, only appeared about 600 million years ago. Why did it take so long? One theory is that complex life requires oxygen, which didn't become abundant in Earth's atmosphere until photosynthetic bacteria had been producing it for billions of years. Another theory is that complex life requires a certain level of energy availability, and it took a long time for ecosystems to reach that threshold. For a rogue planet, the energy available is likely to be less than on Earth because there's no sunlight. Chemosynthetic ecosystems on Earth are less productive than photosynthetic ones. There's less energy to go around, so there's less biomass, fewer organisms, and less potential for evolutionary innovation. A rogue planet might have life, but it might be limited to simple, single-celled organisms. On the other hand, we don't know what we don't know. Life might find ways to harvest energy that we haven't thought of. Evolution is creative and unpredictable. Given billions of years, life on a rogue planet might evolve complexity through pathways we can't anticipate. Another consideration is panspermia, the idea that life can spread from one world to another. If life arose on a planet orbiting a star, and that planet was later ejected to become a rogue planet, the life would come along for the ride. As long as the planet retained its warmth and its subsurface ocean, the life could survive and continue evolving, even though it was now drifting through interstellar space. This scenario seems quite plausible. If rogue planets are as common as we think, and if life arises on a reasonable fraction of planets, then there could be many living rogue planets in the galaxy, each one a biosphere unto itself, drifting through the darkness, but harboring complex ecosystems beneath their frozen surfaces. The possibility of life on rogue planets has profound implications. It means that habitability is not restricted to planets in the habitable zones of stars. It means that life could be far more widespread in the universe than we thought. And it means that when we search for life beyond Earth, we shouldn't limit ourselves to looking at planets orbiting stars. We should also consider the dark wanderers, the rogue planets drifting through the galaxy, warm and potentially alive. Of course, all of this is highly speculative. We have no evidence of life on rogue planets, no biosignatures, no detections of any kind. But the fact that it's possible, that the physics allows it, is enough to motivate further exploration. And if we do someday detect life on a rogue planet, it would be one of the most profound discoveries in human history, proving that life is not tied to stars, that it can thrive in the darkness, and that the universe is even more full of wonder than we imagined. As we look to the future, the study of rogue planets is poised to become one of the most exciting frontiers in astronomy. New technologies, new missions, and new ideas are converging to make what was once impossible now possible. We're on the verge of being able to not just detect rogue planets, but to study them in detail, to understand their atmospheres, their interiors, and possibly even to search for signs of life. One of the most ambitious ideas is to send a spacecraft to a rogue planet. This would be an interstellar mission, far more challenging than anything we've done before, but not impossible. If we could identify a nearby rogue planet within a few light years of Earth, we could potentially send a probe to study it up close. Such a mission would take decades or even centuries with current propulsion technology, but new concepts like laser-driven light sails or fusion rockets could dramatically reduce travel time. A light sail is a spacecraft propelled by a powerful laser beam from Earth, pushing on a large, thin sail and accelerating the spacecraft to a significant fraction of the speed of light. A probe using this technology could reach a nearby rogue planet in a few decades, send back data, and revolutionize our understanding. What would the probe do once it arrived? It could take images of the planet from close range, mapping the surface and looking for signs of geological activity. It could study the atmosphere, if there is one, measuring composition, temperature, and weather patterns. If the planet has a subsurface ocean, the probe could potentially deploy a lander that would melt through the ice and release a submersible to explore the ocean below. This is similar to concepts being developed for exploring Europa and Enceladus, but applied to a rogue planet. The technical challenges are immense, but they're not insurmountable. The main barriers are cost, time, and political will. An interstellar mission to a rogue planet would be one of the most expensive scientific projects ever undertaken, likely costing tens of billions of dollars and requiring decades of preparation and execution. But the scientific payoff would be extraordinary, potentially answering some of the most fundamental questions about life and habitability in the universe. Even without an interstellar mission, we can learn a lot from remote observations. The next generation of telescopes will be able to detect and characterize many more rogue planets than we know of today. They'll measure temperatures, atmospheres, and possibly even surface compositions. They'll search for variability that might indicate weather, rotation, or geological activity. They'll look for biosignatures in the atmospheres of the most promising candidates. One of the most exciting prospects is detecting aurorae on rogue planets. Just as Jupiter has spectacular aurorae caused by charged particles interacting with its magnetic field, rogue planets might have aurorae too. These would be visible at radio wavelengths, or possibly in ultraviolet or X-ray light. Detecting aurorae would tell us that the planet has a magnetic field and that it's being bombarded by charged particles, possibly from cosmic rays or from interactions with the interstellar medium. Another prospect is detecting thermal emission variations across the planet's surface. If a rogue planet has active geology, like volcanoes or cryovolcanoes, those features would be hotter than the surrounding surface and would show up as bright spots in infrared images. By mapping the distribution of hot spots, we could learn about the planet's internal heat distribution and geological activity. There's also the possibility of detecting moons around rogue planets. This would be incredibly difficult with current technology, but future telescopes might be able to do it. If we found a moon, especially one that showed signs of tidal heating or geological activity, it would be a prime target for further study and possibly even a mission. The search for biosignatures is perhaps the most tantalizing prospect. Biosignatures are chemicals or patterns that are produced by life and that we might be able to detect from a distance. On Earth, oxygen is a biosignature because it's produced in large quantities by photosynthetic organisms. For a rogue planet, different biosignatures might be relevant, like certain combinations of gases that are difficult to produce through non-biological processes. Detecting biosignatures is challenging because we have to rule out all possible non-biological explanations. A gas that we think is a biosignature might turn out to be produced by some geological or chemical process that we didn't consider. But if we found multiple biosignatures together, or if we found a pattern that was very difficult to explain without invoking life, that would be strong evidence. The future of rogue planet exploration is not just about the planets themselves. It's also about what they tell us about the universe. If rogue planets are common, and if they're often warm and potentially habitable, it changes our estimates of how common life might be in the galaxy. It expands the number of places we think life could exist and increases the chances that we're not alone. It also raises philosophical questions. What does it mean for a world to be alive if that world has no sun, if its inhabitants have never seen starlight, if they live in eternal darkness? Would such life be fundamentally different from life on Earth? Or would it be similar because life everywhere follows the same chemical and physical principles? These are questions we can't answer yet, but they're questions worth asking. And as we explore rogue planets in the coming decades, we'll get closer to answers. We've come a long way in our exploration of rogue planets, these mysterious worlds that drift alone through the galaxy with no sun to light or warm them. We've learned that these planets are not as rare or as dead as we once thought. They're everywhere, billions of them scattered throughout the Milky Way, and many of them are warm, glowing with infrared light, defying the cold darkness of interstellar space. We've explored the sources of their warmth, the primordial heat left over from their violent formation, the steady fire of radioactive decay deep in their cores, the insulating blanket of thick atmospheres, the possibility of tidal heating from moons or companion planets. We've seen that these heat sources can keep a planet warm for billions of years, long enough to maintain subsurface oceans, to drive geological activity, and possibly even to support life. We've met specific rogue planets like PSOJ 318.5-22, a young, hot world with an atmosphere and a magnetic field, proof that planets without suns can be dynamic and complex. We've examined the physics of how planets cool, how atmospheres trap heat, and how internal processes generate warmth. We've looked at computer simulations that model these processes over billions of years and that predict what we should see when we observe rogue planets. We've also ventured into more speculative territory, imagining subsurface oceans teeming with chemosynthetic life, ecosystems that have never seen sunlight, but that thrive in the warmth from below. We've considered whether life could arise on such worlds, whether it could evolve complexity, and whether we might someday detect it. And we've looked to the future, to the new telescopes and missions that will find thousands more rogue planets, that will study their properties in detail, and that might, just possibly, find evidence of life on a world without a sun. The story of rogue planets is still being written. We're in the early chapters, still figuring out the basics, still making the first discoveries. But already, these worlds have challenged our assumptions about what planets can be, where warmth can come from, and where life might exist. The universe is not a cold, dead place with occasional pockets of warmth around stars. It's a place where warmth can exist in unexpected places, where planets can generate their own heat, where life might find a way even in the darkest corners of space. This should change how we think about our place in the cosmos. Earth is not just one planet among billions. It's one of countless worlds, some orbiting stars, some drifting alone, each with its own story, its own potential. Some of those worlds are warm, even without a sun. Some might be alive. When you look up at the night sky, remember that between the stars you see, invisible to your eyes, there are planets. Rogue planets, warm planets, worlds that might have oceans beneath their frozen surfaces, worlds that might harbor life in their dark depths. They're out there, drifting through space, defying the cold, carrying their warmth with them like a secret. We found a planet with no sun, and it's still warm. And that warmth tells us that the universe is full of possibilities we're only beginning to imagine. That nature is more creative than we give it credit for, and that the search for life and warmth and wonder should never be limited by what we think is possible. The darkness is not empty. It's full of hidden worlds, warm and waiting, and our journey to understand them has only just begun.